السلام عليكم. إن شاء الله هنتكلم النهاردة على الأمبليتود مودوليشن. بعد ما اتكلمنا في المحاضرة الأخيرة بتاعتنا على عملية المودوليشن أو اللي احنا سميناها التعديل، اتكلمنا على التعديل أو المودوليشن في الكونتينوس تايم. غطينا بعض الموضوعات المهمة جدا زي الخصائص بتاعة التعديل. اتكلمنا على عملية التحليل أو الأناليسيس اللي بيحصل للموديوليشن في عملية الموديوليشن لما استخدمت كارير سيجنالز مختلفة، سواء كانت كومبلكس اكسبوننشال كارير أو سواء كانت سينوسويد كارير. اتكلمنا على الخصائص اللي هي البروبرتيز، واتكلمنا على الأناليسيس بتاعة عملية الموديوليشن لما كانت سينوسويد ركزنا عليها جدا وشفنا ازاي نفكها لتو تيرم من الاكسبوننشال سيجنال، شفنا فورير ترانسفورم ليها. اتكلمنا على التعديل المتزامن او السينكرونس موديوليشن والاسينكرونس موديوليشن، وكمان خدنا في الاخير التعديل او تعديل النطاق احاد الجانب اللي احنا كنا بنسميه سنجل سايد باند موديوليشن. تعالوا بقى نشوف الأول كده يعني إيه amplitude modulation مع مجموعة من الأجهزة.
Well, today we have a chance to put away the equations and have some fun. With me is Professor Sandy Hill from the University of Massachusetts at Amherst. And Sandy, maybe you could just give us a quick tour of what we have here.
Okay. We'll be dealing with about 4 instruments today. 2 of them generate signals and 2 of them display and analyze signals. The first, and perhaps simplest, is simply an RC audio generator that will put out a variety of wave shapes, and we'll look at that in a moment. Over to the right is a device that will allow us to study amplitude modulation and the various flavors of it. Down below is a standard oscilloscope to look at the signals in the time domain so we can see their shape. And then finally, the spectrum analyzer will analyze the signal into its Fourier components and will display those, so you get to see the spectral content of a signal.
Now, we'll be seeing all of these in a fair amount of detail as we go through the demonstrations, but maybe we can begin just with the signal generator.
Okay. Let's look quickly at the various buttons involved. There's a lot of flexibility with this device. The top 3 buttons here allow us to change from one simple waveform to another one, a sine wave, triangle wave, square wave. And right below it is a button that will allow us to change the size of the signal. Moving over towards the left, we can change the DC offset, which is varies the signal, the level upon which the signal rides.
And we'll be using that actually when we demonstrate amplitude modulation.
That's right. And then finally, there's a way of changing the frequency of the signal, either changing it by a factor of 10 or a vernier adjustment if you want very specific adjustments, very delicate changes.
Okay, so maybe we can just vary some of this and see what a little bit of it looks like.
All right. What we have displayed at this point is the effect of pushing the sine wave button, and so displayed down here is a 500 hertz sine wave. In fact, let's listen to that.
Great.
And the scope is set to have 1 millisecond for each division here. By varying the amplitude knob, you can make the sine wave smaller or larger. Ear isn't too sensitive to that. By changing the DC offset, it simply rides on a different level. It's like putting a battery in series. And changing the frequency, you get a very perceptible change. A lower frequency, it takes longer to sweep through a period. Higher frequency, it takes a shorter amount of time. And also we can change the wave shape itself from a sine wave to a triangle wave. And you notice that has a richer sound to it. And then finally to a square wave, which is an even brighter sound.
Okay, and actually, as you realize from the previous lectures, with the triangle and square wave with the same fundamental as the sine wave, the richness comes in because of the higher harmonics in the Fourier series representation. Okay, well, let's go back to the sine wave, and we'll use that to take a closer look at the spectrum analyzer.
Okay.
We'll look at a block diagram of the spectrum analyzer shortly, but first let's just look at a few quick things to get a feel for it. We have, of course, the time domain display of the sine wave, and the spectrum analyzer gives us a frequency domain analysis and display, and the vertical axis is the amplitude, the horizontal axis is frequency, and as it's set currently, the frequency axis goes from DC, 0, up to 2 kilohertz, and that, of course, can be varied on the spectrum analyzer. And since we have a sine wave input, we get, as we would expect, a line spectrum corresponding to the frequency of the sine wave. Now, in fact, we can measure that frequency because the spectrum analyzer has a cursor associated with it, which I've just enabled. And this line is the cursor line. There is a readout for the frequency and a readout for the amplitude. And let's position the cursor on the frequency of the sine wave. And we're getting close. And there we are at the frequency of the sine wave. And we can read out, in fact, that it's 500 cycles, and this is the amplitude, and of course you could verify the frequency also in the time domain display simply by measuring the frequency or the period.
This is set at still 1 millisecond per centimeter, so that is 500 hertz.
Okay. Well, now maybe what we can do is vary the frequency. Let's vary the frequency of the sine wave generator. Maybe also listen to it.
I'll turn on the tone, yeah. Okay, I'll make the frequency higher, and you'll see a correspondence in the time domain. Frequency clearly goes up, and that line of the spectrum also migrates up away from the cursor.
Okay, and let me just point out again that this is the cursor line. This isn't a spectral line. And this is the frequency content of the sine wave.
We can also change the amplitude of that line by making the sine wave itself smaller. And you notice the
and in fact,
intensity of it.
While you do that, let me just position the cursor, if I can, on the sine wave. And now as you vary the amplitude, we should in fact see this vary.
That's right.
Okay, now, as Sandy varied the frequency, he did it slowly, and we saw the line move as a single line. Maybe now, Sandy, you could vary the frequency more rapidly, and what will happen is that, in fact, what we'll get if
There'll be a spreading as we go.
Let me turn the cursor off, and what we'll see is a spreading of the line, so that the frequency content is richer, and in fact the analysis of this is considerably more complicated. It corresponds to frequency modulation, where Sandy is now the modulating signal.
That's right.
And we won't really be going into issues of frequency modulation in any more detail in this demonstration.
Right.
بعد ما شفنا ازاي بنغير في الامبليتيود نتيجة عملية الموديوليشن، تعالوا بقى نبص على البلوك دياجرام بتاع السبيكترم انالايزر. البلوك دياجرام بتاع مين؟ بتاع السبيكترم انالايزر، او اللي احنا بنسموه محلل الطيف او محلل الاطياف. محلل الطيف ده هو اللي احنا بنوضح بيه شكل الاشاره في الفريكوانسي دومين. اللي احنا بنوضح بيه شكل الاشاره فين؟ شكل الاشاره في الفريكوانسي دومين. السبيكترم انالايزر تم انشاؤه بواسطه واحد اسمه روكنال، او بيسموه روكنال سيستمز موديل فاست فورير ترانسفورم 512 اوفر اس ريال تايم سبيكترم انالايزر. الفكرة الأساسية ورا الريال تايم سبيكترم انالايزر هو أخذ عينة من شكل الموجة اللي داخلاله وتحليلها إلى شكل رقمي، ثم تحويلها إلى الطيف اللي بيتم حسابه رقميا باستخدام ما يسمى بالديجيتال كمبيوتر أو المايكرو بروسيسور. لذلك هنلاقي في البلوك دياجرام للسيستم ككل هنلاقيه بيتكون من لو باس فلتر تمرير منخفض. احنا بنستخدم اللو باس فلتر اللي هو بيسموه لو باس فلتر 120 ديسيبل اوفر اوكتيف. الاوكتيف زي ما هنشوف هو بيضرب في 8 او بيقسم على 8. بيتم استخدام اللو باس فلتر في عملية السامبلينج او اخذ العينات. ليه؟ عشان يقلل من العيوب اللي بيتم ادخالها اثناء عملية السامبلينج. عملية السامبلينج لسه هنتكلم عليها كمان محاضرة او 2، لكن عشان اعمل سامبل لويف فورم لاي سيجنال جايالي واحولها لديجيتال فورم، هتطلب الامر ان يكون اولا شكل الموجة منخفض او امررها على لو باس فلتر. لذلك استخدمنا اللو باس فلتر في الاول هنا بعد الاشارة الداخلة على طول. هيظهر بعد كده ان انا بستخدم اللو باس فلتر عشان امنع التشويش او ما يسمى بالانتي الياسنج فلتر. يبقى بمنع التشويش او ما يسمى بالانتي الياسنج اللي هو عدم تداخل الاشارات. بعد كده خارج اللو باس فلتر بتاعي هيتم تحويله الى سيكونس عن طريق ما يسمى الكونتينوس تو ديجيتال كونفرجن او اللي هنسميه دلوقتي A to D converter. وبالتالي هينتج عني سيكونس X of N من السامبل. هيديني سيكونس من السامبل او هي الاوريجينال سيجنال لكن عند N سامبل اشيل كل N واحط NT. هو NT هي السامبلنج تايم او السامبلنج انستنت. يبقى السيجنال دي هي سيكونس. السيكونس ده هو نفس الإشارة الأصلية لكن معمول لها سامبلنج. يبقى هو نفسها السامبلز اوف اللو باس فلتر للانبوت سيجنال. بعد كده هناخد السامبلز اوف اللو باس فلتر بتاع الانبوت سيجنال دي اللي خرجت لي اللي هي اكس اوف ان اللي هو السيكونس اللي خرج، وهدخلها على ما يسمى بالديجيتال ميموري. هخزنها على ديجيتال ميموري. بعد كده هستخدم الارثماتيك بروسيسور او المايكرو بروسيسور ده او ديجيتال كمبيوتر عشان يحسب السامبلز اللي موجودة في هذه الميموري، وبالأخص هيحسب الفورير ترانسفورم للسبيكترم اللي كان داخل. بعد حساب السبيكترم أو فورير ترانسفورم عن طريق المايكرو بروسيسور بتاعي، يا إما نحط الكمبيوتد داتا في نفس الميموري أو نحطها في ميموري تانية. يبقى بعد ما بيحصل داتا بروسيس هيطلع لي كمبيوتد داتا. الكمبيوتد داتا او الكمبيوتد سبيكترم اللي خرج ده يا اما هخزنه في نفس الميموري يا اما هروح احطه في ميموري تانية. بعد كده هعيد الديجيتال سيجنال دي لشكلها الاصلي. هعيد الديجيتال سيجنال لشكلها الأصلي في الكونتينوس تايم عن طريق إن أنا أحط ديجيتال أو discrete to continuous conversion، أو اللي احنا بنسميه دلوقتي اللي هو الدي تو اي converter، عشان أروح أرجع سيجنال تاني للإشارة الزمنية المتصلة عن طريق الديفايس ده، سواء كان بيسموه digital to continuous أو digital to analog converter. وفي النهاية هنعرض الكونتينوس تايم سيجنال على شاشة زي اللي احنا شفناها دلوقتي في العرض بتاعنا اللي احنا بنسميها الديسبلاي. لذلك الفكرة الأساسية هي إن الانبوت ويف فورم يجي بعد كده أدخله على لو باس فلتر عشان نعمل لها فلترنج ويشيل التشويش، أو بسميه أنتي أو إلياسنج، وياخد منها عينات عشان يقلل العيوب أثناء عملية السامبلينج ومنع التداخل بين السيجنال الأصلية وبين الكارير سيجنال. بعد كده هندخل الخرج على ذاكرة رقمية أو ديجيتال ميموري. بعد كده هعمل لها ديجيتال كومبيوتيشن عن طريق ان انا ادخلها على ديجيتال كمبيوتر او ادخلها على مايكرو بروسيسور اللي هو هيكمبيوت الفورير ترانسفورم، هياخد السيجنال دي يكمبيوت الفورير ترانسفورم ليها اللي هو احنا بنشوفه على الشاشة بتاعتنا في الاخير، بس بعد كده هيدخلها الاول على دي تو اي كونفرتر او ديجيتال تو كونتينوس كونفرجن. يبقى اللي بيتم حسابه هو السامبلز اوف ذا فورير ترانسفورم. اللي بيتم حسابه هنا هو مين؟ هو السامبلز للفورير ترانسفورم. على سبيل المثال لو كان عندنا انبوت سيجنال، الانبوت دي كانت هي عباره عن ريكتانجولار بالس اللي هو الشكل المستطيل ده، زي ما قلنا قبل كده بيبقى عباره عن نبضه مستطيله اللي احنا بنسميه ريكتانجولار بالس. هيكون فورير ترانسفورم له زي ما شفنا قبل كده هو ساين اكس اوفر اكس. فاللي احنا بنشوفه على الشاشة هو مجموعة سامبلز معرفة عن discrete frequencies. اللي احنا بنشوفه على الشاشة عبارة عن ايه؟ هو عبارة عن مجموعة من السامبلز معرفة عند ايه؟ عند discrete frequencies. ده لو كان الانبوت هو عبارة عن سكوير ويف. لو كان الانبوت عبارة عن ريكتانجولار، اما هنا لو كان الانبوت عبارة عن سكوير ويف هنلاقي السبيكترم انالايزر هيولد لي فورير سيريز كوفيشنت او ما يعادلها من الهارمونكس اللي هي مرتبطة بالسكوير ويف زي ما شفنا في النظر اللي احنا قلناه قبل كده. دلوقتي خلونا نرجع ونبص على الايه السبيكترم انالايزر ونشوف شكل الخرج بتاعه عامل ازاي.
We'll look at the square wave through the spectrum analyzer shortly, but first what we have is what we saw before, which is the sine wave, and just to point out again the fact that the sine wave spectrum, of course, is just a single line corresponding to the fundamental frequency. And here we have a frequency scale now that goes from 0 to 5 kilohertz. And this is then the 500 cycle sine wave. And in fact, we can flip the cursor on, and I happen to just magically have it positioned correctly, and we see that it's a 500 cycle sine wave.
Might be interesting, Al, to go and look at a richer set of signals, such as the triangle wave and the square wave, things that are conveniently on the signal generator itself. I'll switch over to a square wave now. And what you see is all the harmonics coming up, being displayed.
Okay, it's actually interesting to point out, I think, that that the square wave, as we know, is an odd harmonic function, and so, in fact, the even harmonics are missing in the square wave. So this is the fundamental, this is the third harmonic, fifth harmonic, etc. And then the amplitude of the square wave decays proportional to 1 over f, which is the kind of analysis that we've gone through in looking at Fourier series.
Right, and if we switch to the triangle wave, instead of their decaying as 1 over f, the harmonics decay as 1 over f squared, and you see they drop off much more quickly.
And again, of course, it's an odd harmonic signal, and so the even-numbered harmonics are missing. And maybe just to kind of emphasize the point, we can show the sine wave again and the square wave again.
We'll go through from the most bland to the richer to the richest.
Okay, and it's really kind of interesting and dramatic to see the harmonics pop in.
While we're at the square wave, let me fiddle with the frequency of the square wave, and we can see the duality of the time and frequency domains. That is, as you compress things in the time domain, such as this, going to a higher frequency square wave, the harmonics wander further away from each other.
So this is the fundamental. The second harmonic is missing. This is the third harmonic, and of course the fifth.
And as we take this to an extreme, by going to very low repetition rate square waves, all those harmonics come scurrying in and cluster together near DC.
Kind of fun with Fourier transforms. Well, speaking of time and frequency scaling, recall that we had demonstrated time and frequency scaling previously with the glockenspiel. And what we had done there was to record a particular glockenspiel note, and then we played that back at half speed, and what we had done in that case is expanded things in time, consequently compressed them in frequency, and so comparing that with a note an octave lower, then we saw that in fact the time scaling had led to a frequency scaling. And then we also played the same note back at twice speed, and in that case the frequencies were all scaled up by a factor of 2, and again we illustrated that by comparing with the glockenspiel note a full octave up. Now when we did that, we didn't actually look at the time waveforms or spectra, and having the equipment that we have here gives us kind of a nice opportunity to do that. So what I have is the tape that we had originally made of the glockenspiel, the original note that we recorded, and what we'll do is look at the spectrum of that and then compare that spectrum when we play the tape at half speed and also play it at twice speed. So let's play the tape, and what we have is the glockenspiel right now displayed on a frequency scale from 0 to 5 kilohertz. Let's just change that to 0 to 10 kilohertz. So here is the spectrum. Over here we have the time waveform. And here is then the first spectral line, and we can see where that is by setting up the cursor, and magically once again I have the cursor positioned in just the right spot. The first spectral line is at 1.775 kilohertz. And so this is the spectrum then of the original glockenspiel note. All right, let's stop the tape and rewind it. And now what we want to do is play that back at half speed. Played at half speed, the frequencies should be scaled down, and in particular, then, the first spectral line should be at a lower frequency. So let's play that now.
These are really very complicated signals, aren't they?
They really are. Here we have the first spectral line, and we can compare that with the first spectral line that we had before, which was at 1.775 kilohertz, and once again you see that the time waveform over here has been scaled by a factor of 2. So once again we see that time and frequency scaling really works. Incidentally, as Sandy pointed out, and rightfully so, the glockenspiel really is a pretty complicated signal, as a graduate student and I found out when we were preparing the original glockenspiel demo.
Speaking of complicated signals, Al, one of my favorites is to look at speech. I've set this up so that what's coming into my microphone is indeed what you're going to see on the two screens. The telephone company thinks of speech basically in terms of bandwidth, that it extends from about 300 hertz to 3300 hertz. But as we'll see in the spectrum analyzer, there's a lot of leakage outside of that. The telephone company just filters out everything outside of that and thinks of that as a speech signal, so it doesn't have the high fidelity that you might have on hi-fi equipment. As we look at the scope, again, the time waveform is extremely complicated. Seems to have some periodicities in it, although they're short-lived, and then it goes on to some other periodic chunk. And over in the frequency domain, you can see as we extend from 0 to 10 kilohertz that as I speak, there are transients that have spectral content in them, covering that entire band. I can try some simpler signals. A whistle is almost a sinusoid, but as you'll see, isn't terribly sinusoidal. That's the best I can do. I can sing a little bit embarrassedly of bee and boop and things like that.
You don't ask me to sing.
And then different vowel sounds have a lot of energy in, like the letter A, whereas some of the others are very impulsive, like S or P and T. And it's a little hard to grab them at the right time, but what's fascinating is just to stare at equipment like this and try different speech sounds, and you begin to get sort of a sense of the complicated nature of them.
Okay, well, that's a look at some spectra, signals, and now what we'd like to focus on is the modulator and talk a little bit about modulation and demodulation and demonstrate it. And let's begin that by first taking a look at a block diagram of the modulator system.
دي كانت نظرة سريعة على أطياف بعض الإشارات أو السبكترا سيجنالز اللي احنا عرضناها. عايزين بقى نركز دلوقتي على الموديوليتور ونتكلم بسرعة عن عملية الموديوليشن والديموديوليشن. خلينا نبص الأول على الهيكل بتاع عملية الموديوليشن. زي ما قلنا المرة اللي فاتت إن الأمبليتيود موديوليشن بيتكون من الإشارة اللي بعمل لها موديوليشن. الإشارة دي بضربها في الكارير بتاعي اللي أنا محتاجه. قد يكون كومبلكس اكسبوننشال كارير، قد يكون سينوسويد كارير. هنا بنضربها في سينوسويد كارير كوساين اوميجا سب سي انتو تي. قلنا ان السينوسويدال امبليتيود موديوليشن ممكن ادخل الكارير على السيجنال بتاعته واعمل لهم موديوليتنج واطلع الخارج، وممكن كمان اقدر احقن بعض الكارير سيجنال مع الكارير الأصلية بتاعتي. فبالتالي الكارير الأصلية بتاعتي بعد ما كانت كوساين أوميجا سب سي انتو تي، فأنا أقدر أعمل لها انجكتد ب كارير سيجنال تانية هي عبارة عن A اللي هو كونستانت فاكتور مضروب في نفس الكارير اللي هو كوساين أوميجا سب سي انتو تي. بالتالي لو بصينا على الموديوليتور اوتبوت اللي هي واي اوف تي، هلاقي اننا رياضيا اضفنا ما يسمى بالدي سي اوفست او الكونستانت فاكتور للموديوليتنج سيجنال. ليه؟ لان الآلة الاكس اوف تي هضربها في الكوساين ترم هيديني هنا اكس اوف تي كوس اوميجا سب سي انتو تي، لكن كوس مضروبه برضه في A ومجموعه على الخارج، يبقى بالتالي هيديني هنا A كوس اوميجا سب سي انتو تي. وبالتالي الخارج هيبقى عباره عن هاخد كوس مشترك هيتبقى لي A بلس اكس اوف تي. لو نفتكر لما اتكلمنا على الحتة دي قلنا إن فكرة حقن ناقل أو عدمه مرتبطة بمسألة إحنا عايزين نعمل asynchronous modulation ولا synchronous modulation. وكان الاسynchronous modulation متوافق مع الاستخدام البسيط اللي احنا كنا لكاشف في الأظرف اللي احنا كنا بنسميه ايه؟ corresponding to simple use of an envelope detector. كنت بخليه يتتبع مين؟ يتتبع الانفلوب بتاعي. خلينا نشوف اتنين من الويف فورم اللي اتكلمنا عليهم المرة اللي فاتت. الشكل اللي قدامي ده كان نتيجة لقيمة معينة من اختيار ال A حيث A بتساوي A1 وال A هي كانت كارير. الكارير ده اللي عملنا له انجكشن مع الكارير سيجنال بتاعتنا، والويف فورم ده كان لقيمة تانية من الكارير اللي أنا حقنته مع الإشارة اللي أنا بعمل لها موديوليشن، لكن قيمته كانت أقل من الكارير الأولاني. ناخد بالنا إن القيمة لما قلت لقينا إن الويف فورم ده بيتوافق مع موديوليتور بيسمى 100% موديوليتور موديوليشن، وده كان بيتوافق مع 50% بيعمل لي موديوليشن بنسبة 50%، أما التاني كان بيعمل لي موديوليشن بنسبة كام؟ بنسبة 100%. ناخد بالنا إن عملية الموديوليشن اللي احنا عرضناها من شوية على الأجهزة هي نفسها الشكل اللي هو قدامي ده اللي احنا بنسميه موديوليتنج سيستم. البلوك دايجرام اللي بيمثلها هو الشكل اللي قدامنا ده. الشكل اللي قدامنا ده عبارة عن ايه؟ الشكل اللي قدامنا ده بيقول ان الاكسترنال موديوليتنج سيجنال اللي انا كنت بدخلها اللي هي الاكس اوف تي، بلاقي الاكسترنال موديوليتنج سيجنال دي انضربت في الكارير بتاعي اللي طالع من الفانكشن جنريتور اللي هو ده، وكمان في إمكانية إن أنا أحقن كارير إضافي اللي كنت بسميه A variable gain اسمه A، واللي هينضاف في الأخير على الموديوليتد سيجنال في الخارج هنا في الأوتبوت. لما كنت بقول A plus X into cos، وده بدوره هيأثر على الموديوليتد اوتبوت بتاعت السيجنال بتاعتي، وبالتالي يمكن أن يكون الموديوليتد اوتبوت عبارة عن نسبة مئوية متغيرة، حيث يتم تغيير الموديوليشن بنسبة مئوية اعتمادا على قيمة الانجكتد كارير اللي هو قيمة الاي اللي انا حقنتها هنا دي. ناخد بالنا كمان بالإضافة إلى السينوسويد موديوليتور ممكن استخدم كمان السكوير ويف موديوليتور ككارير، وممكن استخدم التريانجل ككارير، وبالتالي انا عندي هنا فانكشن جنريتور زي ما شفنا في الفيديو. اقدر بكل سهولة استخدم السينوسويدال كارير واستخدم السكوير ويف كأنه كارير موديوليتور، وممكن استخدم التريانجل كما لو كان كارير موديوليتور. الشكل اللي قدامي ده هو البلوك دياجرام للموديوليتنج سيستم اللي احنا بنتكلم عليه دلوقتي. تعالوا نروح للأجهزة عشان نشوف عملية الموديوليشن دي بتتم ازاي، وازاي ببدأ استغل البلوك دياجرام ده في الناحية العملية عشان اشوف شكل الموديوليتد اوتبوت بقى شكله عامل ازاي.
Well, Sandy, maybe to begin, you can just point out what some of the controls are on the modulator box.
Okay, there are some interesting points to look at here. This is an input for an external signal. We'll be taking a signal right out of the signal generator and putting it in here, and that will be the signal that will be modulated according to the carrier. The carrier is generated internally in this device, and there are several ways of controlling it. One is the amount of carrier injection. One is the waveform of the carrier itself, and this is typically sinusoidal in the broadcast industry, but others are interesting to look at as well. The output that we'll be displaying on both the spectrum analyzer and scope comes out here. And then farther over to the left, there are some knobs for changing the frequency of the carrier signal.
Okay, let me also just point out again for emphasis that changing the carrier level, as we've talked about, is mathematically equivalent to changing the DC level of the modulating signal, and that's also what affects the percent modulation, as we had just discussed. Now, what we have set up is a sinusoidal modulating signal and a sinusoidal carrier, and as usual, we have the time waveform displayed here, and so this is the modulated signal. And then on the spectrum analyzer, we have the spectral display, and this is the carrier signal, that's the carrier frequency, and these sidebands then correspond to the sidebands associated with the modulating signal. So this is the spectrum of the total modulated output, right?
Right. It's interesting to vary some of these parameters. You can see the sinusoidal modulating shape at this point. Let me switch that to a triangular shape. And again, it's a little hard to sync in both the modulating signal and the carrier, so you see the carrier kind of wandering by, but there it is. Another thing that can be varied is the amplitude of the modulating signal. I'll make it smaller. You'll see the sidebands go away until finally we have a pure sinusoidal carrier. As I bring them back in, again, this is triangular. There would be harmonics there that maybe they're a little hard to see in the spectrum analyzer. I'll go back first to a square wave modulating signal, which is, again, you can see the square wave on top and one on the bottom.
And so all of this then represents sidebands, is that?
That's right. Those are the sidebands due to the square wave modulation. Going back to the simplest, the sinusoidal carrier, another thing we can do is to vary the frequency of the sinusoidal signal that's modulating it. I'll make it higher, and you'll notice that the sidebands wander away from the carrier signal in the spectrum. The spectrum, the carrier signal of that is, doesn't have a frequency that's changing as I do this. It's just the width of the band due to the modulating signal.
So this is the carrier, and these are the sidebands.
That's right. And as we go out very far, those sidebands get gobbled up by the carrier itself. I'll come back to a nice, reasonable point there.
Okay, now we can change also the carrier frequency and, as Sandy has indicated, various parameters. Now, let me just point out, since I didn't previously, that the frequency scale that we're looking at here is a frequency scale out to 20 kilohertz. And we had talked about, or Sandy had indicated, that we can change the carrier signal shape. And let me change the carrier signal from a sine wave to a square wave. Now, you haven't seen any change on this particular display, but let me change the frequency scale, and what you see now is the modulating signal showing up around harmonics associated with the carrier. And those harmonics will go away when we go back to a sinusoidal carrier.
This is actually called a ring modulator. It's very simple to multiply a signal by a square wave. It's just a chopping process. And so a square wave carrier signal is very convenient to generate, and then you simply filter out the higher order harmonics.
Right, I'll go back to the scale that we had before, and Sandy had also commented that we can change the carrier level, and let's do that. on the modulator box. We could do that either by changing a DC offset on the modulating signal or by changing the amount of carrier that's injected. And as we decrease the amount of carrier, in fact, going down to no carrier at all or almost no carrier, that's suppressed carrier. We have only the two sidebands, and the signal is now highly overmodulated. We bring the carrier back up, and when we do that, then we are reducing the percent modulation, and simultaneously, obviously, related to that is changing the carrier level. Now, I had indicated previously that in previous lectures that reducing the carrier is efficient in terms of power transmission, but requires a synchronous demodulator, whereas if there's carrier injected, as we have here, so that we're not overmodulating, the percent modulation is less than 100, then because of the shape of the time waveform, as you can see here, you can do the demodulation with a more or less simple envelope detector. And in fact, a envelope detector of the type that we've talked about before is exactly what is used in AM radios because of the fact that it's so inexpensive. And so here the power transmitted required is higher, but the demodulator based on using an envelope detector is considerably simpler. Well, speaking of AM radios, what we'd like to now demonstrate is modulation and demodulation with an AM radio, which Sandy happens to have here. And let's see, I guess what you're going to do, Sandy, is take it apart for us, right?
Right. I've taken off the back, and I'm just now going to slip out the guts of it all and try and set it up so you can see it conveniently, such as right there.
Now, this is your daughter's radio that you promised to give back.
I would say was my daughter's radio. And now I'll start attaching clip leads, because what we're going to want to do is to be able to see the signals coming out of the radio. We want to see both the audio and then the modulated signal and try and see them on the oscilloscope. So I'll start setting that up now.
Okay, let me, while you're doing that, also just comment that the kind of AM radio that we're looking at here is called a super heterodyne receiver, and the way that it does the demodulation is not exactly the way we've talked about it in the lectures. It's very close. The idea is that the RF signal, the radio frequency signal, first gets modulated down to what's called an IF stage, the intermediate frequency stage, and then it's that signal that goes through an envelope detector of the type we've talked about to generate the demodulated signal. So I guess what Sandy has some probes on are the RF input and a ground. And
that's right. The red lead here is a ground. It's common for both the signals we'll be looking at. This is at the audio. We're actually looking at the signal going directly into the speaker across these two leads. And then this probe down here, which I found by hunting and pecking, is the IF signal, the intermediate frequency signal, with a station on it that I'll now try and get something that sounds reasonable.
Tonight at the NCAA.
Okay, a little sports.
Never quite know what you're going to get when you turn this on.
That's right.
We've got some high thin clouds around here, the northern fringe of a large storm that's clobbering the southeastern United States.
Make some adjustments there. And what you can see right here is the audio signal. I'll give it a little bit more gain. And this is the actual intermediate frequency modulated by the audio. And there's a correspondence between them that goes by awfully fast, but I think is pretty simple to see.
So basically the top trace is the envelope of the bottom trace.
That's right. This is what comes out of the envelope detector, and this is the signal into the envelope detector in this particular radio. What I'd like to do for a last experiment is what we've been doing at this point. I'll turn this off for a moment. Is we're taking something that's coming in over the airwaves, as they used to say, and we're simply viewing it. What I'd like to do now is generate our own radio frequency signal, tune it up so this radio is going to hear it, whatever that means, and display it here. What we're going to do then is use the audio oscillator along with the amplitude modulator, and we're going to take from the output now the lead here, and this will act as the antenna. This device was not designed to put out a lot of power, but fortunately we don't have a lot of distance to go over. What I'm going to do is turn myself into an antenna. I'm basically 150 pounds of salt water, and when I touch this, the signal coming in here, which is radiating a little from the wire, is going to suddenly radiate from my whole body, and hopefully will be enough to be picked up. So what I'll do is I'm going to turn this on. Excuse the noise. Now, I've set this up so it's tuned to a particular radio station, and I hope I can find it now. It takes a little fussing. That's not it. That sounds like it now. Okay.
So this gets billed as Sandy Hill Human Antenna. Right?
That's right. What you're looking at here is I've got the antenna at this point, and what we're going to do is you're seeing the audio signal. This is coming from the signal generator up here, and this is the intermediate frequency signal again. You can hear it's much stronger when my body becomes the antenna. And I'll leave it on for a second, and I can switch to square wave. Doesn't look much like a square wave. Various things. There's significant distortion because of all the transformations that the signal is going through. But it does indeed work, and we're picking up a frequency that the radio is tuned to.
So Sandy has now been modulated and demodulated.
That's right.
Well, hopefully all the things that we've gone through in the process of this tape and this set of demonstrations gives you a feel for at least some of the things that we've talked about so far in the course. And Sandy, I'd really like to thank you for joining us, for sharing your insights with us, as well as sharing your equipment with us. Thanks a lot.
It was a treat. Thank you.